So, let's talk some exponential and logistic modeling type problems. So, let's get out of the, here's the equation, graph it, and do stuff with it, figure this stuff out. And let's get into some real world modeling of stuff. Okay? So, suppose that you rake your yard. And before you get the rake hung up in the garage, there are 50 leaves on the ground. And you know what I would say then? I wouldn't use those necessary words though. Okay? I might drop a few naughties. Okay? Especially if I just got done raking the yard and then more leaves fell on the ground. Okay? Okay? The number of leaves continues to increase by 8% every hour. Find the number of leaves on the ground after 12 hours, or 12 hours after you finished raking. Okay? So, we get done, and then we turn around and we look, there's 50 leaves on the ground. Okay? 1 hour later, 1 hour later. 1 hour later. Ha, ha, ha. How many leaves are on the ground? Is my question. How many leaves on the ground 1 hour later? Daniel says 54 leaves on the ground 1 hour later. Anybody concur with him? Anybody get something different? Anybody care? What do we got? Well, they're still figuring it. Tell me how you got 54.
So I took 50 and then I multiplied it by 1 because it needs its initial value.
Okay.
And then plus the 8%, which is 0.08.
So really you multiplied it by 1.08.
Yes.
Right? Okay. And from that you got 54. Okay? That's one way of doing it, and that is correct. Okay? We can multiply it by 1.08 because that includes the initial 50 leaves that are on the ground, along with the extra 8% on there. Okay? The other way is you could multiply 50 by 8%. So 50 times 0.08, and you would get 4. So there would be 4 leaves that get added on in that hour, bringing your total to 54. Okay? I like Daniel's method because it includes that 50. I don't have to do that extra step of adding the 50. Okay? Alright? So, next hour, you got done watching a movie. You look out your window. Uh-oh, how many leaves are on the ground now? What do you got, Dylan?
Approximately 58.
And that, because you really get 58.32, right? Okay. How did you come up with 58.32, approximately 58?
I took the 54 and I multiplied it by the 1.08.
And that 54 was actually 50 times 1.08, and then you multiplied that by another 1.08, right? Yeah, I love that. Okay? So let's say then you went back and you watched your favorite TV show. So now it's 3 hours later. Approximately how many leaves are on the ground? We'll round to 2 decimal places here in this case. Ailey, what'd you get?
62.98.
62.98 or 62.99, whichever one. Yep. Okay. 62.9. Well, I'm going to go 99 because it's 9856. So that was 50 times 1.08, and then times 1.08, and then times 1.08. 8. Right? Okay? Do we see a pattern developing? Bless you. Do we see one? Okay. Could we make a leaves based on number of hours after we finished raking equation? Kua, you were shaking your head yes. You got one for me?
You can do the 50 times 1.08 and then to the next one of whatever your hours is.
So we'll call that T in this case? Love it. Excited for it. That helps us because now I don't have to go times 1.08 to get 4, then times 1.08 to get 5, and then times 1.08 to get 6, and so on and so forth until it's times 1.08 to get 12, right? Okay. So we can do this here, and we can say that this is 50 times 1.08 to the 12th power. Yes? So 50 times 1.08 raised to the 12th power should get me 125.909 leaves. Now, logic dictates here, can I have 0.9 of a leaf on the ground? I mean, it could be broken, but a broken one would be considered like a leaf, right? Okay. What if this were people? Would I have that debate of could there be 0.9 of a person? No, it's a whole person, right? Okay. So when you get to the end of these modeling problems, you gotta stop, collaborate, and listen, because ICE is back with a brand new edition. Okay? Right? So you got to think a little bit about this stuff. Okay? And you got to determine, okay, can I have decimal points in this problem? Can I not? Here, you know, it's a leaf. I probably would accept 125.9 or 0.91 or 0.909. Or if you wanted to just say 126, I'd accept that. You know, it's this one I would be more lenient. But if it were a person problem, heck to the no. Okay?
So would you still round up for those people, or would you round down then?
Either way. Yeah, again, that's the whole leniency part. Yep. Okay. Usually, though, I would round up because that decimal point then, you know, would be. Okay. All right. So, if a population is changing at a constant percentage rate, okay. Now, here on this particular slide, it says each year, but really, this could be over any time frame. Okay? As long as the change is in that same time unit. What I mean by that is I could have a percentage population changing every day, and then it would be how many days out. It wouldn't have to necessarily be a year. Okay? So we can rotate that through to whatever it is. But more importantly, okay, P sub 0 is my initial population, T is my time, and R is my rate as a decimal. So like in that last problem, we had an 8% increase, so that's why we went 1.08. We added it. So here, we add if it is increasing, because that would give us then an exponential growth. Our B would be bigger than 1. And here we subtract if we are decreasing. Okay? Which then would give us a B value less than 1, which would be a decay. Okay? So, determine the exponential function with an initial value of 12 and increasing at a rate of, 3.5% per year. So this 12 is my P sub 0, my initial value. Increasing means that I'm going to go with plus 3.5% is going to be 0.035 in a decimal. Move that decimal point 2 spots to the left to get it into a decimal. Okay? So my initial function P of t is going to be P sub 0 times 1 plus or minus r to the t becomes 12 times 1. Oops, excuse me. No, I can go. Let me go. Colorfulness. 12 times 1 plus 0.035 to the t power. Okay? So that would end up being, my P of t would end up being 12 times 1.035 to the t power when it's written out nice and condensed, and then we don't have to do any extra work. Okay? Based off of that function, so what would the population then be, let's say, 28 years, or 28 time units later? 12 times 0.035 raised to the 28th power gets me I get 31.4421. Concur? Yeah? Okay. Love it. All right. The example of all examples. Okay? Example number 3. So let's say you are rocking it back in the 80s and 90s. Okay? All right? And you're cruising through the mean streets of Duluth, Minnesota in a 1979 Ford Pinto. Okay? Now, what's wrong with the Pinto? Anybody remember what was wrong with the Pinto?
The gas tank.
Where was it?
I don't remember where it was, but I just know a lot of them would blow up.
It was way in the back. It was right behind. It was right in front of the rear bumper. So if you got hit from behind, it punctured your gas tank, and it sent and then if there was a spark, because obviously in a crash there's probably going to be a spark or some kind of a flame, and then your car blew up. Okay? All right? Not good. Okay? Design flaw.
Was this your car back in the day?
Just you wait to see whose car this was back in the day. Okay? Mind you, I grew up in Wisconsin. Okay? So, back in 1985, okay, you and Marty McFly, he bought a DeLorean, you bought a Ford Pinto. Okay? Valued at $1,800. You went down to the used car dealership and you said, I want that rockin' Pinto. Just wait till you see this rockin' Pinto. Okay? It was a classic. White with red striping, Starsky and Hutch style. Okay, when you guys are doing the problem, I'll pull up the picture of the Starsky and Hutch car. Okay? It was all the talk of Greenway High School. Okay? Hard to believe, but somehow that hot rod actually lost value at a rate of 7% each year. Okay? Find me an exponential function that describes the value of this classic hot rod, and 2, find the value in 1990. Okay? Just so you know what rocking it out, that's what rocking it out is. Okay? I'm not going to tell you who that is. Okay? But there's only one of us on this team That's female. That's all I'm going to say. So, again, that's the Starsky and Hutch car. I forgot to record this while we were showing it, okay? Cherry red Gran Torino with the swoosh down the side. Okay. Little reverse on the colors, but hey, still rocking it, okay? All right? So, couple of things that we need to find in the problem. First off, what is my P sub 0? 1800. This value right here is my P sub 0. Okay? Is this classic car gaining value every year or depreciating in value every year? It's depreciating because it says right here that we are losing value, so that's going to mean minus sign there. At what rate are we losing out on money? 7% is my R, so that's going to equal 0.07, okay, in decimal form. Okay? So my function, we'll call it P of T, is going to be 1800, that's my P sub 0, times 1 minus 0.07 to the T power. So in answer to my first question of find me an exponential function, P of T is going to equal 1800 times 0.93 to the T power. Do we all agree with that? Okay. All right. So based upon that, then we are asking the second question here is, what is the value of this rockin' red and white Pinto in 1990? So 1990 is how many years after 1985? 5 years. So my T value here is 5. Okay? So 1800 times 0.93 raised to the 5th power gets me 1,252.24 dollars. So $1,252.24. Really, on my calculator, I got 1,252.23906,474, but logic told me we're talking a monetary value. I can round that to the hundredths or to 2 decimal places. Okay? Right? So when money is involved, 2 decimal places for sure. Again, it's that logic coming in. If this were the amount of rides that I was giving to all my friends because they wanted to ride in this classic rocket of a street rod, then we would round up to the nearest whole number or round down to the nearest whole number, because you can't give 0.24 of a ride. You're either getting the whole deal or you're not getting it at all. Okay? All right? Handle? All right. So, exponential growth and decay models. So, we have our standard, regular, old, run-of-the-mill exponential growth and exponential decay. Okay? And then we have our, if it's base E. And if it's base E, we call that one that's our continuous growth or decay model. Okay? So if it's continually, it's always increasing. Okay? Always. It's not just we get to a certain point and then it increases or decreases. And then we go another time frame and then we get to a certain point and then it increases or decreases. It is continuously increasing or decreasing. Now, making both of those different kinds can be done. First off, if I start with 15 milligrams and it doubles every 6 days, okay, so then after 6 days, how many milligrams would I have in my culture? I'd have 30. After 12 days, how much would I have in my culture? 60. Okay. The downfall with that is, what if I need to know how many milligrams is in my culture in 2 weeks, 14 days? 14 is not a multiple of 12. You know what I mean? Okay. So we have to be able to come up with one. So I will deal with the blue one first. Okay. So initial mass of the culture is 15. So that means, what is my A value? 15 is my A. It's my initial value. Okay. Now, I need to find my B. Well, we did this last week. Okay. We said if I need to find my B, then 30, I'm going to use this second point here. 30 is my Y value. A is 15. B is what I'm looking for. What is X? From this second line, what is X? If 30 is Y, what is X? What is X? 6, because I'm using this line. So that's B to the 6th power. Okay? I need to solve for B. What am I going to do first? Divide by 15. 30 divided by 15 is 2. So I get 2 equals B to the 6th power. I still need to solve for B. How am I going to solve for B? No. Because my exponent is not, has the variable.
Take the 6th root
I'm
on
going to
both sides.
take the 6th root on both sides. And if I take the 6th root on both sides, that gives me the 6th root of 2, if I want it to be exact, or 1.12246 if I wanted to round. And if I'm rounding here with B's, remember we go out as far as we can. So that would give me an exponential model. P of t would equal 15 times 1.12246 to the t power. And t is in days. Not 6 days, just days. So I could use that model to figure out 14 days down the road. Okay? Alright? That's one way of doing this particular problem. Okay? The second way of doing this particular problem is using our continuous growth formula. Okay? So again, my initial value, whoa, that's a nice little hook I made there, but my initial value is 15. Okay? It's what I started with, 15. Now, instead of finding B, I need to find K. So I'm going to use this second line in my data points. And I'm going to say that Y is equal to 30. A is equal to 15. E is Euler's constant. K is what I'm looking for. And X now is 6. Again, divide both sides by 15. 2 equals e to the 6k power. Now my variable is in the exponent, so I have to use logs to solve it. So I'm going to take the natural log, because that's log base e of both sides. The natural log cancels out on this left side. The natural log cancels out the e, so that leaves me with the natural log of 2 equals 6k. So I divide that by 6, and I get k. The natural log of 2 divided by 6 is 0.115525 is my k value. Agree? So my function here then would be P of t equals 15 times e to the 0.115. Whoa, tap the brakes. What's going on there? 1155525 t power. And again, t is in days. Okay. Now, there is one other way to do this that I don't recommend, okay, but I will show you here right now. And that third way is, because it doubles every 6 days, I can have a b value of 2, right? Because that would be a doubling value, okay? And then my t would be in 6-day increments. Okay? So my p of t here would equal 15 times 2 to the t power, but t is 6-day increments. So meaning, if I wanted to use this one right here, if I wanted to use the second one, I would have t be equal to 1, not 6. If I put t equals 6 into that function, I'd get where it would be at 72 days. Okay? All right? Now, what I would like you to do in the remaining time that we have is, I would like you to verify that you get the same answer on all 3 functions based off of this data point, based off of the second or the third data point that we came up with. So verify that you get 60 if you put in 12 in the first one, verify that you get 60 if you put 12 in the second one, and verify that you get 60 if you put whatever you need to put in the third one. Okay. So there they are. If we verified them. Why are these first two not exact? Let's say you first.
They deal with decimals.
Why do they, what?
It's because the values that we plugged in, the decimal values are rounded.
We rounded here. Yep. So when you round early, you're going to get a little bit off, but you'll be close. Okay? All right? Tomorrow we'll hit up logistics. Have a great day.